Time feels simple. We remember the past. We experience the present. We move toward the future. A glass falls and shatters. It never unshatters. Smoke rises from a fire. It never gathers back into wood. Everything around us seems to agree on one fact. Time moves forward. But here is the strange part. The fundamental laws of physics do not care about direction. If you record two billiard balls colliding and play the video backward, the motion still obeys Newton's laws. The equations work both ways. At the level of basic interactions, gravity, electromagnetism, even quantum mechanics, the mathematics does not insist on a preferred direction of time. And yet, our universe does. So why? Why does time move in only one direction? To answer that, we need to separate two ideas. The laws of physics describe how particles move. But time's arrow describes how processes unfold. There is a difference. At microscopic scales, individual particles collide and interact in ways that are mostly reversible. But when billions upon billions of particles interact together, something changes. Consider a simple example. Imagine a box divided into two halves by a wall. On one side, there is gas. On the other side, vacuum. If the wall is removed, the gas spreads out evenly to fill the entire box. This always happens. Gas never spontaneously gathers itself back into one half. In theory, if every molecule randomly moved in exactly the right way, the gas could return to its original state. But the probability is so unimaginably small that it effectively never occurs. This is where the concept of entropy enters. Entropy is often described as disorder, but that is an oversimplification. More precisely, entropy measures the number of microscopic arrangements that correspond to a macroscopic state. There are vastly more ways for gas molecules to be spread out evenly than to be confined neatly in one corner. So systems naturally evolve toward states with more possible configurations. Toward higher entropy. The second law of thermodynamics states that in an isolated system, entropy tends to increase. And this increase defines the arrow of time. A broken glass has higher entropy than an intact one. There are many ways for shards to lie scattered. There are very few ways for them to assemble into a perfect glass. Time moves from lower entropy to higher entropy. This seems to solve the mystery. But it creates a deeper one. Why did the universe begin in a state of such low entropy? If entropy always increases, then in the distant past it must have been lower. And at the very beginning, at the Big Bang, it must have been extraordinarily low. The early universe was hot, dense, and surprisingly uniform. Matter was distributed almost evenly across space. From a thermodynamic perspective, that uniformity represents low entropy in a gravitational system. Gravity complicates entropy. For most systems, spreading out increases entropy. But for systems dominated by gravity, clumping increases entropy. Stars, galaxies, black holes, these structures form as matter collapses, releasing energy and increasing the total number of possible configurations. The early universe had not yet clumped. It was smooth, which means it had room to become more disordered over time. In other words, the arrow of time may exist because the universe started in a very special state. But why did it start that way? Physics does not yet provide a definitive answer. Some cosmologists suggest that inflation, a rapid expansion in the early universe, set initial conditions that made low entropy possible. Others propose multiverse scenarios where our universe is one of many, and low entropy beginnings are rare but inevitable somewhere. The truth is still uncertain. There is also a psychological arrow of time. We remember the past. We do not remember the future. This asymmetry aligns with entropy. Memories are physical records stored in the brain. Creating a memory involves increasing entropy in the environment. Information storage requires energy dissipation. We remember events that have already increased entropy. The future has not yet left physical traces. So we cannot remember it. There is a cosmological arrow of time as well. The universe is expanding. Galaxies move away from one another. Space itself stretches. If the universe were contracting, would time feel reversed? Most physicists believe that even in a contracting universe, entropy would continue increasing. Time's direction appears tied not to expansion alone, but to thermodynamics. Quantum mechanics introduces further subtleties. At the quantum level, many equations are time-symmetric. But when measurement occurs, when a quantum system interacts with the environment, something irreversible seems to happen. Wave functions collapse. Possibilities become outcomes. Some interpretations argue that collapse is not fundamental, but apparent. Others suggest that decoherence, interaction with the environment, effectively locks events into one direction. Even here, the arrow of time emerges from interaction and complexity. There are rare phenomena in particle physics that violate certain symmetries. Some processes involving weak nuclear interactions show tiny differences between forward and backward time behavior. These violations are subtle. They do not fully explain why glasses shatter but do not reassemble. But they hint that time asymmetry may be embedded more deeply than classical thermodynamics suggests. The most profound mystery may be this. At the microscopic level, time may not fundamentally flow. The equations of relativity treat time as a dimension, similar to space. Past, present, and future coexist in a four-dimensional space-time structure. From this perspective, the flow of time is not a property of the universe. It is a feature of consciousness. We experience time sequentially because our brains process information sequentially. We move along a world line in space-time, perceiving events one after another. But the universe itself may simply exist, all at once. This idea is known as the block universe. In it, time does not pass. We pass. And yet, entropy still increases along our path. Even if all moments exist, the direction from low entropy to high entropy defines what we perceive as forward. So why does time move only one way? Because the universe began in an unlikely, low entropy state. Because statistical mechanics favors disorder. Because gravity amplifies asymmetry. Because information storage requires energy dissipation. Because complexity grows. Time's arrow may not be fundamental. It may be emergent, like temperature emerging from molecular motion, like pressure emerging from collisions. The direction of time may emerge from probability. In a universe governed by statistics, certain processes are overwhelmingly more likely than their reversals. And overwhelming likelihood feels like inevitability. There is a final, unsettling possibility. If the universe continues expanding forever, entropy will continue increasing. Eventually, stars will burn out. Matter will decay. Black holes will evaporate. The universe will approach maximum entropy, a state sometimes called heat death. At that point, no significant processes will occur. No gradients. No structure. No complexity. Time will still exist. But nothing will happen. The arrow will persist, but there will be nowhere left to go. Until then, we live in a universe far from equilibrium. Energy flows from stars to planets. Chemical reactions build complexity. Life emerges and evolves. We are products of time's arrow. Creatures shaped by increasing entropy. And yet, capable of asking why it exists. Perhaps the most remarkable fact is not that time moves forward. It is that we can notice it. The laws of physics may be symmetric, but the universe is not. Somewhere, at the beginning, conditions were set that allowed entropy to rise. And from that rise came stars, galaxies, chemistry, biology, memory, and thought. Time moves in one direction because the universe was born with room to change. And change is the essence of time.